Welcome back to the fourth and likely final segment of the combined section 2.4 and 2.5. As I said previously, this last bit is one example that I want to pull out of section 2.5 only because it has there's some interesting algebra in the solution to this problem, and it's not really it's not too much of a stretch. I'd expect you to be able to reproduce this sort of result, maybe in a test situation or whatever. Unfortunately, the way that most people approach this problem is they don't really remember how to solve the problem. They kind of memorize the formula to solve it, which seems, it is what it is. But anyways, it's kind of it's an interesting setup, and there's a couple of homework problems that are attached to it. You just have to be real careful about which side is which and what exactly is going on in it. But let me move over here and kind of set up the geometry, the sort of diagram of what's going on, and then we can talk about a strategy, because it does become algebraic, which sometimes it's been a while since people have done any significant algebra. And the reality is, when you take a college algebra class, even though you have certainly discussed the idea of different variables and everything else, it sometimes is a bit of a challenge for students to work with more than one variable in an equation and say, well, what is it I'm really trying to do? So let me just kind of set up the problem. I'm going to draw this a little bit bigger. So let's say that, and this is an example where this does actually happen. I'm going to start without, some of these problems we've had like terrain issues or whatever, but let me just start with something that's relatively flat ground. And suppose there's some sort of a really, really tall, like, tree or something like that, maybe at the top of a water tower. But for whatever reason, it's not practical to find, to be able to like measure horizontally, right? Like the trunk of the tree might not be directly over the highest point. Maybe if it was a water tower, you're looking at some antenna. Maybe there's no way to find exactly where the bottom is. So you can't really do this distance sort of thing. But what you could do is you could stand out here some distance away, unknown distance, in fact, and measure an angle to the top of the tree. Okay. And let's say that you're interested in the height above ground, so we'll call that h. And so you've got some angle above the angle of ascent, which we'll call alpha. And then you walk closer to the tree, and then you make another measurement, again, an angle of ascent of beta. Now, you don't necessarily know, remember, you can't really figure out where the physical center of the tree is anyways. So this distance is unknown, at least it's not measured. But supposing we did measure this distance from the one position where I measured to another position, and at this point, this problem is solvable. Okay, you can, if you have d alpha and beta, you can find h. And here's how we're going to do this. We're going to basically solve two triangles simultaneously. So recognize that wherever it happens to be, maybe I'll do a thinner pen. So wherever the direct position is from the top, this is making a right angle, right? So maybe it's a little bit cockeyed, maybe it comes down here, which is not in the middle of the trunk or whatever else. And so that's theoretically what I was talking about, like horizontal versus vertical. You can think about, maybe theoretically that's a right triangle. It's not really something you could physically measure in some other way, but you can measure it indirectly. And what we're going to do, this is kind of a little trick. We're going to create two equations with two unknowns, and then we're going to solve them using some basic algebra skill. So in this situation, we don't know what this distance is, and there's no way to measure it directly, but we could, we could just call it something and know that we're going to use it at some point, but we don't necessarily have to know exactly its value. So when that kind of a situation comes up where you kind of need it as a placeholder, it makes sense to assign a variable to it. So we'll just call that distance x. We don't know what x is. It doesn't actually matter what x is because all we really want is h. So now I'm going to construct two equations that involve the tangent of these known angles, right? So let's start with the easy one, beta. So notice that the tangent of beta is equal to h over x. And I'm going to go ahead and simplify. I'm going to linearize it so we don't have ratios. These are the two. These these are the two unknowns, h and x. We don't know h and we don't know x. So these are our two equations, or sorry, two variables. So I have h is equal to x times the tangent of beta. Okay. Now I can't solve one equation with two unknowns. I need to create another equation, which I'm going to use the much larger triangle, right? And say, similarly, going to say, well, tangent of alpha is equal to h over, now it's not just x, it's actually d plus x. And this is where the problem comes in. People think that you're just supposed to use d, but it's not. It has to be the entire side, right? So d plus x is in the denominator. And the result is that you have h is equal to d plus x times tangent of alpha. Okay, so now we have two equations, two unknowns. How do you solve an equation? How do you solve a system of equations where you have two equations with two unknowns? Well, usually what you do one of two things. Either you do what's called an addition method, or you use substitution. And in this particular case, I think that maybe addition might work. But notice it's kind of convenient because both of these equations are equal to the same variable, right? They're equal to h. So the left-hand sides are equal, so the right-hand sides must be equal. And if I just think about setting them equal to each other, now I will have an equation that only has one variable, which is kind of convenient. So that's going to be my step. I'm going to find x, and then I'm going to substitute it back in here to find h. That's kind of the strategy. So first, find x. Okay, and how I'm going to do it is by saying the right-hand side of this equation is equal to the right-hand side of that equation. So x times tangent of beta, which remember, this is just some number. I know what beta is, so I know what tangent of beta is as well. And it's not the point to calculate it. It's to find a nice compact formula where I don't have to do that over and over and over again. So x times tangent of beta is equal to the quantity d plus x times tangent of alpha. Okay, so if I want to get x, I want to solve for x, then I have to get x by itself. And the only way to do that is to distribute. So I have x times tangent of beta equal to d times tangent of alpha plus x times tangent of alpha. Okay, so now I've got distributed. I need to move everything that's got an x to one side and everything that doesn't have x to the other side. So I'm going to subtract x times tangent alpha from both sides, and I end up with x times tangent of beta minus x times tangent of alpha is equal to d times tangent of alpha. Now I'm going to collect the coefficients on x, so I'm basically factoring out an x. I have x times the quantity tangent of beta minus tangent of alpha is equal to d times tangent of alpha. And then the final step is to divide by the coefficient multiplied by x. So I'm going to divide both sides by this quantity, this tangent beta minus tangent alpha, and I'll just be left with x equal to something. And it's not real pretty, but we have x is equal to d times tangent of alpha over the quantity tangent of beta minus tangent of alpha, right? So, okay, now that I have an expression that describes x in terms of the three known quantities, d, alpha, and beta, I can substitute that back up into this equation and find H. Now I could do it here too, but it's not as convenient because then I have to, you know, it becomes a mess. This is the easiest one because I've just got X times tangent beta. So if I finish this off here, I'll have that H is equal to D times the product tangent alpha times tangent beta divided by the difference tangent beta minus tangent of alpha. And there's the formula that tells me if I know D, alpha, and beta, I can find H, all using right triangles. So let's actually do this with an example, and then we're going to call it quits. This is sometimes in the textbook. There's another problem that's very similar to this that involves like whale watching or something like that. So sometimes this is called the whale problem. At least that's what I've called it. It's the tree problem, whatever. But let's see it actually applied. I mean, that's kind of a messy looking equation. I mean, we'll see ones that are much worse than this. But basically, the thing to remember is these are all just numbers, right? That's a number, that's a number, that's a number, that's a number, and that's a number. We're just going to do some arithmetic to crunch out the height. So real quickly then, I think I'm now on page 8. Okay, so suppose, and let's just pick some realistic numbers. Let's say that the distance is 35 feet. So you took a measurement at some point, and then you walk 35 feet closer to the tree. The angle of ascent at the far distance was 37 degrees, and the angle of ascent at the close position was 51 degrees. So we're going to find H. Okay, so remember, H is equal to D times tangent of alpha times tangent of beta over the difference tangent of beta minus tangent of alpha. So substituting the values, we have, it's going to be 35 feet times, let's see, in the numerator we have the tangent of 37 degrees, tangent of 51 degrees, the product of those two, and then the difference, tangent of 51 degrees minus tangent of 37 degrees. So when we calculate this all out, again, I'm going to start with the more complicated part of this, the denominator, because there's different operations involved. So 51, take the tangent, then subtract from that the tangent of 37. I'm going to reciprocate that. Now I'm going to start multiplying it by the tangent of 51 times the tangent of 37 times the 35 feet. And there's my result. So before I apply significant digits, it's 67.664127 whatever feet. So the question is, how many significant digits does everything have? Here we have one that's got 2, 2, 2. The minimum number, the smallest number of digits for any of the measured values is 2. So the result should be 2. And so our final answer is 68 feet. Okay, so like I said, you may be asked to replicate this result on a test situation, quiz, whatever. You can do one of two things. Either you can memorize the formula, which seems kind of silly because it's not hugely applicable to anything besides this, or you can kind of work on your algebra skill to be able to derive the formula, which can be done, you know, relatively quickly. This isn't a simple problem, but it's also not one that's impossible. Anyways, okay, so that's the last of the material from chapter 2 entirely. We're gonna skip through the book now, and we're gonna move to the first 3 sections of chapter 7, because what we've done at this point is we've kind of exhausted all of the ways in which we can, quote, solve right triangles. The next question is, well, can we solve triangles that aren't right triangles, or what are so-called oblique triangles? And the answer is yes, of course we can. But there are different methods, and we have to derive some specific formulas to do that. So it takes a bit of time. Now, why the textbook doesn't do this at this point is beyond me. When I first learned trigonometry, this was the straight lead in. Once you know how to do right triangles, you might as well do oblique triangles and just have triangles finished. So that's how we're going to do it. There is some disagreement as to whether or not that's applicable. But I really think that from a theoretical standpoint, you should be able to solve all triangles at least by halfway through the semester. And then you can move on to more interesting sorts of results. So I will see you in the videos in section 7.1 next.